We are working on 3.1. In the past, you have been asked many times to find the leading coefficient and the degree of a polynomial. So if I had 4x squared minus 6x to the fifth plus 3x to the fourth minus 7, we asked you find the degree and the leading coefficient. So the degree is going to be 5. It's the largest exponent. And the leading coefficient is the number in front of that term, -6. And then we said, good job, and we moved on, and we didn't tell you anything else about it. And you wondered, why on earth do we care? Well, I'm almost going to answer that question today. Not quite, but almost. So, when we try to model real-world situations, we run into equations that can be really, really complicated. So imagine you are designing some kind of space navigation equipment. And the equation that handled one part of that navigation was really complicated, and it was a graph that looked like, well, that's a bad example. Let's do this. Well, no, that's fine, whatever. Okay. And we want to use that equation to navigate a spaceship around the Earth. Okay? Not super far as space goes. So that equation, we know it, but it's really complicated. Lots of variables and trig and everything thrown together, and it's just a big mess. Well, it turns out that performing calculus on really complicated equations is very difficult, or a lot of the times it's flat out impossible. We just don't know how to do it, or it can't be done. And we've decided we don't like to be beat, and we like to fly spaceships, so we are going to substitute in another equation that's pretty close. It's not perfect, but it's pretty close. So I build an x to the third equation. So I build like 6x to the third plus 2x squared, something. Anyway, I build this x to the third equation, and when I graph it, it looks like this. Not bad, right? Certainly not perfect, but not super bad. And if I'm flying a spaceship around the Earth, that might be good enough. So the actual equation is known, but it's hard to work with. And you guys don't know calculus, but in calculus, we do these calculations called integrals and derivatives. And integrals can be very, very, very hard to do on complicated equations. However, integrals and derivatives are very, very easy to do on polynomials. I could teach a fifth or sixth grader how to do calculus on that polynomial. It's way easy to do. So we've decided we're going to scrap the tough equation and we're going to throw in this polynomial, and then the calculations are really easy. Okay, but let's say I want to take my spaceship to the moon. Would you trust this equation to get you to the moon? Now, the moon's really far away, and right when you're throwing darts, the further away you throw a dart, the harder it is to hit the target, because just a small error is going to leave you way out into outer space. So we scrap this equation and we build a better one. But the better one has to be a lot more complicated. And let's say it's an x to the 150th. And so on. Okay. When I draw that equation, it looks like this. Much better. The equation is a lot longer, and that might freak you out a little bit. It's probably way longer than the real equation. However, performing calculus and other calculations on that polynomial is way easier than trying to do the same calculation on the original equation. And it turns out we can keep making our polynomials bigger, and that will get our equations closer and closer to the true equation. So if we were flying to Mars, then we could scrap this equation and we could create, let's say, probably want to make that a 9. And so on. And if I make this equation big enough, I can get so close to the real graph that you can't tell the difference. Well, you can. Is that exactly perfect? No, it's really close. If I want to be more accurate, I just build a bigger equation. And we could build an equation that had 1,000,000 terms. Okay? The computer in your car that tells the fuel injectors how much fuel to spray into the cylinder on every for every detonation is more complicated than the navigation computer that sent people to the moon. That's just the fuel injection portion of your computer. And it takes into account things like how much air is coming into the engine, how much air is leaving the engine, what's the temperature of the air, how much oxygen is leaving the engine unburned, how much, what's the air pressure outside. Did I say temperature? Anyway, it takes all of these variables and it plugs them into a really long equation and then it does the calculations, but computers have no trouble doing really long calculations super quick. So the reason we study polynomials so heavily is because in the real world, it's much easier to use polynomials to model anything than it is to use the actual equation that would model it. Because calculus on polynomials is super easy. Now, you're never going to see this unless you take at least Calc 2, and most people never get there. But that's why we study polynomials. They make the world much easier to deal with. Okay? Even if this had 1,000,000 terms, a calculator can handle 1,000,000 terms, no problem. And it's much easier to turn a difficult equation into a long polynomial and then use the polynomial. That's why we do it. So, why do we care about degree and leading coefficient? Well, those are the two things that tell us the basic shape of any polynomial. So if I have y equals x squared minus 6, well, let's do 2x squared minus 6x plus 4, this tells me the shape. The other pieces just tell me the position. Okay, what is the shape of this graph? It's a parabola, and it opens up. And is it tall or short? It's tall. Okay, so it looks like this, and then the other pieces are just going to move it around. All right? What if it was negative 2x squared? It's going to open down, and it has the same shape. Okay? Every x squared graph will either open up or down, depending on if it's positive or negative, and then the leading coefficient tells you how far it's stretched or smashed. Okay? It gets a little bit more complicated with x to the third graphs. What does y equals x to the third look like? Well, it comes up, it flattens out at 0, and then it speeds up again. Okay? What if I made it negative? The negative version is going to look like that. Okay? Well, x to the third graphs can have up to 3 roots. So the basic shape is determined by this and that. Okay? And x to the third graphs either go up to the right and down to the left, or up to the left and down to the right. So we kind of have this disco dance going on. I'm not a dancer. Okay? But because it's an x to the third, it can have 3 roots. So it's entirely possible for it to look like this, where it touches the x-axis 3 times. Could it touch twice? Kind of. So if I grabbed it, maybe, and I moved it down, now it only touches twice. It still has 3 roots, right? One of them's positive, and then we have a duplicate negative root. Could it touch just once? Yeah, right there. Could it touch 0 times? No, why not? Yeah, we're doing the disco dance. It's got to hit the x-axis somewhere. Okay? Well, where does this set of wiggles come from? It comes from everything else. So the leading term dictates the direction and the overall shape. And then all the other numbers and variables will figure out exactly where the position is and how many wiggles there are inside. Because it's totally possible for it really not to wiggle at all, and it just does that. Okay? And as a general rule, the more information you have over here, the more wiggles it's going to have. That's not a guarantee, but if there's a lot of information there, there's a greater chance that it has lots of direction changes. Okay. What about x to the 4th? If I graph x to the 4th, it sort of has the same shape as a parabola. It just grows faster. So if you were to graph x squared, it would look like this. And x to the 4th just gets bigger faster because you're multiplying it by itself 4 times. Oh, that's I'm sorry. That's a little misleading. So x to the 4th starts out wide and then grows tall. And then a parabola would look like this. Because if you multiply a fraction by itself, it gets smaller. So this is over 1 up 1. So x to the 4th starts flatter and then ends up taller. And then x to the 6th would start even flatter and go even taller. Okay? But an x to the 4th could hit the x-axis 4 times. So it is entirely possible for an x to the 4th to look like a W. Okay? So what does the degree tell us? It tells us how many times it could hit. Is it guaranteed to hit 4 times? No. Could it hit 3? Yeah, it doesn't have to be symmetric, so that's 4. But this would be 3, and this would be 2, and this would be 1, and that would be 0. So the 4 tells you the maximum number of roots. There is no way this graph can hit the x-axis 5 times. It's impossible. Okay, but it could be 3 or 2 or 1 or 0. Okay. What does this tell me? That it's happy, right? The left side is up and the right side is up. Does everybody understand that? And then where do the wiggles come from? Well, all of the other information will dictate both the position and how many direction changes are on the inside. So it could look like this, it could look like this. It all just depends on what else is in there. So the leading term tells us direction and shape. Okay. What would an x to the 5th look like? Well, if it's positive, what has to happen? It's going to look like this. The left side has to be down and the right side has to be up. Okay. What happens on the inside? All sorts of things could happen. It could do this and not have any direction changes. Okay? It could look like an x to the third. Or it could have 5 roots. We don't know. But I know that the left side is down and the right side is up because it's an x to the 5th graph and it's positive. Does that make sense? Okay. What if I had a negative x to the 16th? So we know down on the left and down on the right. Does everybody understand that? Why are they both down? Because the degree is even and the leading coefficient is negative. That's the basic shape. And then whatever happens in the middle is anybody's guess. You need all the other information. So we don't know the position. We don't know the direction changes. We don't know how many roots. But just looking at the degree and the leading coefficient, we can guarantee that the left and the right sides both go down. And then what could happen on the inside? It could kind of look like a parabola. This one would be a really weird parabola. It would have to go like this and be nearly flat and then come down. Or it could hit the x-axis 16 times or anything in between. Okay? So in 3.1, you only really have 2 questions. And this one says, find the degree and the leading coefficient. So in this case, the degree is 8 and the leading coefficient is negative 20. Super easy. Okay? And then here, you're going to determine the end behavior. So the first one, the degree is 3 and the leading coefficient is positive, so it falls to the left and rises to the right. Okay? What about B? What is the degree? 6, and that tells us it's either a happy or a sad face. And it's sad because the leading coefficient is negative. Okay? What about C? We have to construct the biggest exponent possible. So to construct the largest possible exponent, I need to multiply this times that. So that would give me negative 4x to the third. Right? So that one is going to be up to the left and down to the right. Okay, let's make it a little bit harder. What about So it's going to be this times this times this. So that would be negative 2x to the third. So it would be this one. Okay? All right. What if this was a third power? So that would be negative 2x times negative x times negative x times negative x, which is 1, 2, 3, 4 negatives would be positive. What would a 2x to the 4th graph look like? Up to the left, up to the right. Does that make sense? All right. That is everything in 3.1.